What is light? It took experiments over several hundred years before the fundamental nature of light became obvious. Isaac Newton did some famous experiments in light, including splitting light with a prism into its constituent colors and showing that those colors were fundamental, could be recombined back into white light. Newton argued that light was primarily a particle. He called them corpuscles, but he meant subatomic particles. One of his colleagues, Christian Huygens, however, thought that light best displayed wave properties, was best understood as traveling as a wave. And it turns out that light has both particle and wave-like properties. It seems easy to understand light as a particle because it clearly travels from one place to another and carries energy, as particles do. It's perhaps less obvious that light behaves as a wave. Its fundamental wave-like nature was shown in beautiful experiments by Thomas Young early in the 19th century. In this experiment, called the two-slit experiment, Young took a light source and sent that light towards two slits. Light going through the two slits went to a screen where, to Young's surprise, instead of seeing a smooth gradient of light, he saw an alternating set of light and dark bands, interference fringes. Now that makes no sense at all, because a particle will travel from A to B, and if more particles travel, they will simply add their intensity. But it does make sense in terms of waves. In Young's slit experiment, light coming from one of the slits could correspond to a wave where the trough was at one position, whereas light coming from the other slit was at the peak. The peak and the trough cancel out, leaving darkness. At an adjacent position, the two peaks coincide, and so the intensity doubles. Young's slits and the interference result is only understandable in terms of wave-like properties. Around the same time, other wave-like properties like diffraction were first observed. The fundamental theory of light did involve its wave-like properties. It came from James Clerk Maxwell in the middle of the 19th century. He produced an elegant theory based on 4 equations which related oscillating electric and magnetic fields and showed that those oscillating electric and magnetic fields would travel or create a signal that propagated at the speed of light, 300,000 kilometers per second in a vacuum. This is the fundamental phenomenon of light and also of other forms of electromagnetic radiation, like gamma rays and radio waves. Light, or other forms of electromagnetic radiation, can be characterized by electric and magnetic fields oscillating, and in fact, any time an electric or a magnetic charge is accelerated, it leads to the emission of electromagnetic radiation. And that indeed is how many of those forms of radiation are actually generated. It was Einstein, early in the 20th century, who did beautiful experiments to show that light also had particle-like properties, and had to be fundamentally thought of as a particle too. In the photoelectric effect, which he explained, light liberates an electron from a metal and behaves in such a way as to carry a particular amount of energy, kinetic energy, in a ballistic sense, as if light is a tiny bullet. The word for this light particle is photon. If we want to create a hybrid of the wave-like and particle-like understanding of light, we can imagine light traveling like a wave packet, where it's fundamentally a wave, but the wave is isolated in space and has a finite extent. The energy of an individual photon in these early 20th century experiments is extremely small. An average light bulb is emitting many, many trillions of photons every second. But in subatomic experiments, we can isolate single photons. And the scale that characterizes the energy of a single photon is set by one of the most important constants in nature, the Planck constant. And it was the physicist Planck who first put a number on this. Returning to light as a wave, we can characterize it by 2 attributes, a wavelength and a frequency. If you want to think of an analogy, think of a train passing by a fixed point, which could have boxcars of a particular length. All forms of light and other electromagnetic radiation are observed to travel at the same speed. It's also the speed limit of the universe, the fastest that any signal can travel in the universe. It's denoted by the symbol small c, and it's 300,000 kilometers per second. The frequency of a light wave is how many peaks or troughs pass a fixed point every second. The wavelength is the distance between any 2 peaks or any 2 troughs. So we can see that the product of the frequency and the wavelength equals the speed. We can also see the inverse relationship between frequency and wavelength. Let's use the train analogy. Imagine you have two trains traveling at the same speed, which would be true of any two electromagnetic waves. If one train had boxcars of twice the length, their wavelength would be 2 times longer. But clearly, if they are traveling at the same speed, 2 times fewer boxcars would pass every second, so their frequency would be 2 times lower. So there is an inverse relationship between frequency and wavelength for light or any other electromagnetic radiation. Another fundamental attribute of light or other forms of radiation is how they travel through space from a fixed source, like a light bulb or a star. The way light travels through space follows what's called the inverse square law of radiation, which means the intensity measured at any distance from the source goes down as the square of the distance. So if you have a fixed detector, like a CCD, and you move it outward from a source of radiation, it collects a number of photons, or an intensity of light, that goes down as the square of the distance. Imagine the detector detects a fixed quantity of light. Move the detector 2 times further away, it will detect 1/4 of that amount of radiation. Move it 3 times further away, 1/9, and so on. The inverse square law of radiation is fundamental to how radiation travels through the universe from any astronomical object like a star or a galaxy. Light cannot be understood solely as either a particle or a wave. In some situations it has particle-like properties. It travels from one point to another and carries energy. In other situations it has wave-like properties. It can have the phenomena of interference and diffraction. In the end, we have to understand light as both. Photons is the name for the particle nature of light, and we understand photons to be like a wave packet, where there are still peaks and troughs in an intensity of radiation. The radiation moving out from a fixed light source diminishes with the square of the distance, the inverse square law that underlies how radiation travels through the entire universe from stars and galaxies.